and thinking about what it means to invert a matrix now. Well, inverting a matrix is supposed to do the same thing that inverting a function does. After all, if matrices are just linear transformations and linear transformations are just functions, then to invert a matrix is the same thing as to invert a function. So let's start with some matrix. I don't know, how about 2, I'll try to make this as friendly of a process as possible. Let's just tweak this a little, move it out to 1, 1 instead of 0, 1. There we go. Okay, so here's a matrix. A is equal to 2, 1, 3, 1. And when we talked about defining a matrix for a linear transformation yesterday, the way that we did it was we said that the first column of our matrix is exactly where the vector 1, 0 gets sent to. So in this linear transformation, 1, 0 is getting sent to 2, 3. And likewise, the second column of the matrix is where 0, 1 is getting sent to. So here 0, 1 is getting sent to 1, 1. So now supposing that I want to invert this matrix, what do I want to do? I just want to run this transformation backwards. So instead of looking for a transformation that turns 1, 0 into 2, 3, and which turns 0, 1 into 1, 1, what I really want is I want the opposite. I just want to erase this arrowhead here and draw it on the other side of the arrow. And that is what the inverse of our matrix is supposed to accomplish. So now I'm looking for a matrix which transforms the vector 2, 3 into the vector 1, 0, and which transforms the vector 1, 1 into the vector 0, 1. So that's our goal now, is to find that matrix. And when we find that matrix, we will call it A inverse, if it exists. So let's get this off to the side here. If A inverse exists, I'll just say it that way, then it should satisfy A inverse multiplied by the first column of our original A, 2, 3, had better equal 1, 0. And at the same time, A inverse multiplied by the second column of our original matrix had better equal 0, 1. So it's a bit of a twist, because it looks like we're trying to solve a matrix vector equation here, except that instead of trying to solve for the vector, the purple thing, we're trying to solve for the matrix. A inverse is what we don't know here. So we have to ultimately develop a tool to do that. But before we do it with our own algebra and arithmetic, let's try it with the app. The app has the functionality to do this. So what I'm going to do is just reset this app back to where it began here. Whoops, that's not the reset button. There we go. And now what I'd like to do is take those vectors that we started with, which were 2, 3, and 1, 1, and I'm going to make them my domain vectors instead. So 2, 3, I'm looking in the domain here. Actually, that's 2, 3. And then 1, 1. Nudge this one out a little bit here. 1, 1. There we go. So notice now on the left side and the right side we have the same picture that we had before, just backwards. And so the matrix that's accomplishing this transformation should be the inverse of the matrix we had originally. In other words, because this is doing exactly the opposite of what our matrix was doing a moment ago. Our original A was going this way. That matrix was 2, 3, 1, 1. This one is therefore its inverse. So really, to help the app out here, I should call this A inverse. And there's our purported inverse, -1, 1, 3, -2. We have to talk about how to compute that for ourselves, but before we do that, let's just do the little exercise of verifying that this really is our inverse. And how do you verify that two matrices are inverse to one another? Just multiply them. And see what happens. So the first entry in my product is going to be -1 times 2 plus 3 times 1. The second entry in my product is going to be -1 times 1 plus 1 times 1, otherwise known as 0. Now if I move down a row, the lower left-hand entry in my product is 3 times 2 minus 2 times 3, 0. And the final product, 3 times 1 plus -2 times 1. So how do I know that this was indeed the inverse? What did we get here? It's the identity matrix. So it is. It is the inverse of our A. It worked. The system works here. So this is the transformational picture of what an inverse does. It just does exactly the opposite transformation that the original matrix A did. So that when we form this inverse, and this inverse that we formed here, A inverse times A, this inverse is something that we could then operate on a vector x from our original domain. And if I first follow A and then follow A inverse, I should get back to where I started from, if A inverse undoes exactly what A does. And the reverse should also be true as well, that if I first follow A inverse and then follow A, that I get back to where I started from. So there's the transformation picture. Now let's talk about the computational picture. So how could we have discovered this A inverse matrix for ourselves? So let's rewind the tape here to where we had two facts about our inverse matrix that we knew would make it our inverse matrix. Whoops, need to go further back than that. Maybe I'll just, let's bring it back. Here we go. So down here at the bottom of the screen is what we're hoping for. We're hoping for a matrix that can turn 2, 3 into 1, 0, and can also turn 1, 1 into 0, 1. So if the columns of A inverse, so let's just write A inverse as a shell over here, A inverse has as its columns, let's call them V1 and V2. Then, according to our first equation, we should have 2 times the first column of A inverse, so 2 times the column V1, plus 3 times the column V2, should equal 1, 0. And at the same time, from the second equation, 1 times the first column plus 1 times the second column should give me 0, 1. V1, V2. Let's put some plus and equals in there. There we go. Okay, so both of these need to be true for the columns in order to make it our inverse. But it's looking an awful lot now like we have a system of equations we can solve. In particular, this is a system of equations that we can solve for V1 and V2 just by somehow putting this all together into a matrix and doing some kind of row reduction. But we can't really do that yet because each of these is still a vector equation. So since these are still vector equations, we do a little bit more repackaging. And we take the perspective that here we have a column, and here we have a column to worry about. Here's another column. And the upshot of it is that what we end up with is the ability to solve both of these systems of equations at once using the same process of steps. In other words, what we're going to do is take these two vectors, the right-hand sides of these equations, 1, 0, and 0, 1. And the row reduction that we need to do in order to solve these is going to be done on the same matrix. Namely, it's the matrix A itself on the left, which has the entries 2, 3, and 1, 1 in the columns. And so what we get is a matrix that's augmented, but it's a little bit bigger of an augmented matrix than we're accustomed to working with. Usually we augment a matrix by a vector. This time we're augmenting a matrix by a matrix. And then we're going to try doing the process of row reduction to solve this system. So for a moment, let's remember why this works. We're trying, really, to solve A times A inverse is equal to identity. Here's probably the better way to think of it. A times A inverse is equal to identity. Except that A inverse is made up of sort of two different columns, V1 and V2. And the identity matrix is made up of those columns 1, 0, and 0, 1 on the right-hand side. But when I multiply the matrix A by this matrix that has columns V1 and V2, really what I end up with is a matrix over here which has as its first column A times the first column of A inverse, and which has as its second column A times the second column of A inverse. And if that's supposed to be equal to the identity matrix, then that means two things. It means that A times V1 is equal to the first column of the identity matrix, and the first column of the identity matrix is 1, 0. And that is a matrix vector equation. And we can solve that matrix vector equation by row reducing the matrix A. And when we do that, we would end up row reducing an augmented matrix that looks like this down there at the right, with A on the left and 1, 0 on the right. And then we would get some solution. And when we were finished with our row reduction, that solution would be sitting right here. It would be staring us in the face. It would be the column over on the right, after we've row reduced this part down to the identity matrix. And then this would be V1 in that column.
The other one just kind of goes away.
Well, I'm hiding it for a moment, okay, because I'm making the point that we can solve both of them at the same time, because the system that we need to solve for V2 has the same coefficient matrix, has the same A. The only thing that's different about it is the right-hand side, because the right-hand side now is supposed to be the second column of the identity matrix, 0, 1. So in other words, in order to solve that second system, I would need to solve this augmented matrix. But it's the same matrix on the left, it's just a different vector on the right. So all the row operations are the same, which means in order to find the columns of my inverse, I can do all of this at once. All I have to do is row reduce the augmented matrix until I get the identity on the left. And when I have the identity on the left, I'm going to have my inverse matrix on the right. That's the plan. We need to be able to completely row reduce the left-hand side. And when we've done that, what lives on the right-hand side is our inverse matrix. There's our computational tool. So let's just do it and verify that we have what we expect to have here. So how would you like to row reduce this matrix on the left, this one over here, in order to get the identity? What first step do you want to do?
Divide by half.
Multiply by half or divide by 2. So that if I do that, I'm going to end up with, instead of 2, 1, we're going to have 1, 1 half. But now remember, since we're dividing that row by 2, that we also have to divide the same row over here by 2. Okay, so far so good. And we're grooming this 1 here to be our first pivot. And if that's going to be our first pivot, we need to clear out what's underneath it, subtract 3 times the first row from the second row. So this becomes a 0. Whoops. 1 minus 3 halves becomes negative 1 half. 0 minus 3 halves, negative 3 halves. And 1 minus 3 times 0 remains 1. Now my 1 in the first row is indeed a pivot. And I would like for this negative 1 half to become my next pivot. But before it can become my next pivot, what should I do to it?
Multiply by negative 1 half.
Let's multiply it by, divide it by negative 1 half, or multiply it by 2. In other words, turn it into 1 by multiplying that row by negative 2. And when I multiply that row by negative 2, negative 3 halves turns into a 3, and 1 turns into a negative 2. Now I have my row echelon form with 1s in the pivots. And to get reduced row echelon form, we just need to clear out the column above my final pivot, which has a 1 half in it. And to clear that out, I'm just going to subtract twice the second row from the first row. So when I subtract twice the second row, a half times the second row subtracted from the first row. So here I'm going to have 1 half minus 3 halves, negative 1. And 0 minus a half of negative 2 is positive 1. And when this whole process is done, we've now discovered the inverse of our matrix. It's right there on the right-hand side. So this matrix now is A inverse. And hopefully that was the same A inverse that we saw a moment ago. I certainly hope it is.